Alright guys, starting. Alright, so this is useful to know. Here are the ones that you're expected to memorize. I apologize that you have to memorize these. I wish you didn't, but you do.
Are we going to write that down?
This is it's in your textbook. The chapter that is derivatives of trigonometric functions on page 144. Sorry, page 145, as well as 142. This is already in your text. So unfortunately, you have to memorize these. The ones that are easy, obviously, guys, stop talking. Obviously, is the derivative of sine is cosine. Derivative of cosine is negative sine. I think these two are the easiest. Tangent is, and I'm not exactly how sure you memorize the rest. Yeah, you just have to memorize them. Tangent is secant squared. Secant is secant. Cotangent is negative cosecant squared. And cosecant is negative cosecant cotangent. I don't know any tricks. These two are easy to me, but there is one trick that I do recall on the students mentioning, was that if you take the derivative of one of the 6 basics, and these are all the 6 basic trig functions, if it starts with a c, you can automatically write negative. Right? If it starts with a c, you can automatically write negative.
Oh, that's cool.
That does help a little bit. All right. So let's take a look at.
No, wait.
Okay, wait. Okay, all right. It's in the textbook. Okay.
I know. When you write it down, it helps remember it. Wait, is it secant? Derivative of secant of x times tangent of x?
Yep. That's a dot. Yep.
And if it's also times derivative of cosecant?
Yeah. If I don't write a dot, it's because that's multiplication. Negative cosine of x times the cotangent of x. Yeah. Good question. All right, so there's our given. So we already have a literal equation in terms of x, so we can just go ahead and write f prime of x. We don't have to do implicit differentiation, which we'll discuss in the very near future. So the derivative of tangent of x is secant squared x. This is secant squared x. Okay. Then, okay, so this part I think most of you got. It just gets a little funky when you take the second derivative. So this is where we start discussing chain rule, okay, where we have to look at, and let's remember that this is technically this.
I forgot,
This is the same thing, which will help you see this. So to do chain rule, okay, look at the exponent on the outside, bring it to the front, leave the inside alone, drop this down a power, times the derivative of the inside, of the guts, if you will. Okay? And the derivative of secant is, derivative of secant x is secant x tan x.
October 1st.
Okay, so I'm going to review this again. So I think we're all fine with this. Let's just give it a definition that the derivative of tan is secant squared. And understand, I can say secant squared x that has the same meaning as you can say secant x, that whole value squared. It's just different notation, it means the same thing. It may be, bless you, try to go for the, if you can. Go for the, go for the, yeah. Yes.
Oh, I didn't mean that was gross.
Oh, I'm sorry, Mr. Gross, I'm sorry. All right, so that's f double prime. So now taking the derivative of this, guys, 2 to the front. So this is the chain rule. This is the chapter we're on now. I know some of you were absent, but now we're talking about chain rule, which, if you want to see that, that is the following chapter. I am looking for it right now. Yes. Derivative implicit chain rule is just following this, so it is on page 148. section 3.6. Okay, so if you look at rule 8 on page 149, I think that breaks it down pretty clearly. F of g of x. You can see that you could write it like this and break it up. But okay, just you'll be doing this so much that you don't even have to worry about the mathematical definition. Just know when you have something raised to a power, what you do is you bring that power to the front, drop it down, and then take the derivative of the inside. Okay? You guys have been doing this with power rule, you just didn't realize it. And let me give you an example before we complete this.
Wait, that's the answer?
Nope, wait. Yeah, but just 1 second. We can probably simplify it. But I want to give you a quick example. If you have f of x is equal to x cubed, for example. Most of you, I think all of you should be familiar with this, is equal to what? 3x squared. So 3x squared then times the derivative of the inside of the x. Right? Because this is technically this, if you will. What's the derivative of x with respect to x? Which is 1. So you never really see that you're doing it. When it's something this simple, when it's just a monomial of a single variable, and you're taking the derivative with respect to that variable, you don't see it. But technically that's what's going on. So for here, that's why 2 to the front, drop it down, times the derivative of the inside. And the derivative of secant x with respect to x is secant x tan x. And this, I think, simplifies a little bit more. Of course, I can just write this secant x to the 1 power, which is just secant x. So this is 2 secant x times, this is just a product, so times secant x tan x. When they're written next to one another, it's multiplication. So this fully simplified would be 2 secant squared x times the tan of x.
Okay.
So this was the challenge problem today. This is what you should arrive at. Some of you were absent. Some of you may have missed the chain rule, but that's what we're touching on now.
My question is that why don't you distribute the 2 to the tangent as well? Like why would it be 2 secant squared x times 2 multiplied?
Oh, this is all just a product. This is a product. This is a product. Okay. So what if I took a very similar problem, and I was given, so this is another example, if I had f of x is equal to, and say it's the same trig function tan, but it's tan of, say, 3x squared plus x. And I want to take, let's say, the first derivative. So this is very good for you guys, just practicing problems like these, which I'll be assigning for homework, for good practice. Not to give you busy work, but it's good. You just need good practice for these. So again, chain rule. The big picture, the derivative of tan is secant squared. Okay. So the derivative of this is going to be secant squared of this times the derivative of the inside, which is 6x plus 1.
Now why wouldn't we just distribute the tangent and then find the derivative of the...
You cannot do that. There is some identities or Pythagorean identities and that you want to memorize where tan of a plus b is equal to, again, something that I don't like to memorize,
So
but something, it's not something you just distribute. This is like a function, tangent of this value. It's not like some standard value, like if we were saying, if I had a value, say, of x, I can distribute the x, or a 4, I can distribute the 4. It's not how this works.
So generally, sorry, Kate, when we've got either a trigonometric function within something like this, or a variable is insanely high, that's when we use chain rule?
No, you have to use chain rule every single time. Okay. You didn't know you were using it here, but technically you're using it here.
I understand that, but just the whole process of going through the thought process of bringing the variable to the front and multiplying by the derivative of the inside.
Yep, you have to do that every single time.
Okay.
Okay, so this is raised to the first power. Okay, so if I brought the 1 to the front and then dropped it down, you would see 1 times 1, which is 1. But don't let it get that confusing, okay? It's not tan squared of this, it's just tan of this. So it's secant squared of this times the derivative of the inside. That's it. We'll see more. I think maybe for those of you that are like, wait, hold on. We'll do more and maybe it'll click. Yes.
Could you simplify that, or would you leave it as?
Oh yeah. So could I simplify this? Not really. Yeah. Couldn't really do much here. Yes.
Is there any way you could give us like a worksheet of problems you think that we should be able to do?
Yep.
Alright. Can we do a normal chain rule? Because I need a refresher on like actually like without all these words.
Without the trig function.
Just all
without the trig function.
Yeah, so that's maybe an X.
Because this is a very normal.
I know, but like so words are confusing.
Without the trig function.
Yes.
That's what you want. Okay.
Just like simple.
Yes.
And then one more with trig function.
Yep. That's all we're gonna do today. Okay. So
But I need like
here's another example.
I wasn't there for the
Okay. So let's say you have f of x is equal to. Chain rule without using trig, where you're just not. Probably just want to expand it, but let's say you do.
Let's do 6x squared to the plus 2 plus x. It's getting really complicated now.
Here we go. This will set the example. This is good. This works. Okay. I have some value being squared. Okay. So chain rule says.
See, but I would just square that. Just follow the example.
Duh. Okay. But we're doing this without trig functions. Okay. I know that. My God. We're gonna do both. We're gonna demonstrate that it works. Relax, Mackenzie. Everything will balance.
What about
Universal
to the
balance, I
six?
promise. What's that?
Like what about to the 6? Because then I wouldn't expand it. Well, okay,
What
let's
about
do
to the
final,
six?
like 3x squared to the 6.
Beautiful. Thank you.
Yeah, you're gonna expand that?
I would not expand it.
It can be whatever power you want it to be. It could be pi if you want pi.
Let's do pi.
So we're gonna go with this guy. Okay. Here we go. So 6 to the front, 3x squared. Drop this down a power. Now times the derivative of the inside. Did you say you're so confused? Okay.
That's an answer.
And you multiply the 6x to the 6, right?
Okay. So I wanted to do something more simple so I could show you both ways so you can see that it works. But this would be a premise. Of course, we can definitely simplify this if you wanted to punch that into a calculator. 3 to the 5th.
So
243. Yeah. So 243 times 6 times 6, or times 36, is 8748.
That's a 4 number.
Oh, sorry. Oh no. Thank you. Yes. Now it should make sense that this guy is 1 degree less than this guy because it's the derivative of a polynomial. So this is x to the 12th term, so it should be x to the 11th. Yes.
Okay, so I understand how chain rule works, but I don't understand how we use it on the one who just did the tangent dx squared plus x.
The derivative of tangent of anything is secant squared of that times the derivative of x. Now the reason you don't see it for the example in the book is because what's the derivative of x? Yeah, and that's why I don't like these as much as when they use u, because u is more clear. So that being said, let me write it out so that it works for anything. So this is the way you really want is this. d dx of say something of let's do sine of u, where u is just some value. Okay, we don't know what it is. But the big picture is this, that this would be equal to the cosine of u times du dx. So this is the big picture. It's saying, okay, cosine of whatever that is times the derivative of the guts. Right? So this is the big picture here. I actually prefer that they use this in your text because it lets you see everything. But of course, you don't see it for sine of x because the derivative of x is just 1, so you don't see it. The same principle is why you don't see it for here. Drop it down, the derivative of x is 1. You don't see it because of x. So this is the key on this slide here. This is the key here. Is that to get the big picture, it's the derivative of sine of u would be cosine of u times the derivative of u in respect to x. It's the derivative of u.
So if we had like 2x squared sine, the derivative of that would be 4x.
Let's do this. Let's keep doing some examples here. We'll keep doing some examples. So if I want to find so if I have, say, y equals the sine of 3x squared plus x, okay, then y prime would be equal to the cosine of this times the derivative of u with respect to x, which would just be 6x plus 1.
Okay, that makes sense.
Now, the second derivative is going to be pretty long. It's going to be a product rule. It'd be.
We don't have to do it.
We don't have to do it? Okay, teacher. We don't have to do it. We don't have to do it.
It's not mandatory.
All right, so we're talking about this. So, let's see here. Look at some more problems. So something like example 7 is something you should be comfortable with. On page 152, it says, example 7, how much time do we have? Got plenty of time. Awesome. Finding slope, part A. Find the slope of the line tangent to the curve y equals the sine of x to the 5th power at the point where x equals 1/3 pi. B, show that the slope of every tangent line to the curve y equals 1 over 1 minus 2x cubed is positive. Okay, let's go piece by piece. So this is page 152, example 7. And part A.
Why don't you just write 3 in my paper?
Find the slope of the line tangent to the curve y equals sine of x to the 5th power at the point where x equals 1/3 pi. So in other words, we want to find f prime of pi over 3. Right? Because if we find the derivative of y, that gives us the slope of any tangent line, right? And then I say, okay, well, what's f prime at this specific point? What's the slope of the tangent line at x equals pi over 3? That's what we're looking to find. Okay, that's what we're looking to find. So this is what we want. Let's go piece by piece. Let's just go with, if we have y equals sine of x to the 5th power. Then y prime would be equal to bringing the 5 to the front, dropping it down a power, and then times the derivative of the inside, which is derivative of sine of x, which is cosine of x.
Wait, you're not including the 4 in that.
Okay.
Wait, how did
So
that
again,
happen?
if it helps, you can think of this as sine of x to the 5th power. Okay, so that I think this is probably an easier way to understand it. 5 to the front, drop it down, and then the derivative of the inside, which is cosine of x. Okay, so this is y prime of x, so to be more specific, so we see the connection here. So this is y prime of x, and so we want to find y prime of pi over 3, which would be equal to 5 times the sine of pi over 3 to the 4th power times the cosine of pi over 3. It is useful to know that if you forget, I'll typically do my triangles if you forget like what sine of pi over 3 is. A lot of students, I think they memorize the degrees, which is fine, because that's sine of 60, and cosine of pi over 3 is cosine of 60. You can do your 30-60 triangles off to the side, you know, to get an exact value. Your typically the calculators, like the TI-83s, 84s, I think they're programmed to give decimal values. I don't know if there's a way for them to give you radical values, which these will contain, at least this one will.
Can we use the,
So y prime of pi over 3 would be equal to 5 times, now sine of 60, if you forgot, is going to square root 3 over 2. And this is to the 4th power, times the cosine, sorry, we'll just go ahead and simplify it. So the cosine of 60 or the cosine of pi over 3 radians is 1/2. And so this equals, so y prime of pi over 3 radians, or 60 degrees, would be equal to, they get 45 30 seconds. It's a really sad looking 5. Let's correct that. Alright. That would be the answer to part A. That would be the slope of the line tangent to the curve, y equals sine of x to the 5th power, at the point where x equals pi over 3. Of course, if you have it in terms of pi, then this would be radians. You don't have to write the radius in RAD or write radians. Then it should be radians.
can we use the yellow calculators for the calculation?
I know you are permitted to use the TI-83 and TI-84, but I'm not showing you by the yellow calculators. Yeah, if there's one for me with the an 83 or an 84.
I can go grab one. Do we have to
So anyway, what's that? You don't have to know the inner circle, but for this, I typically like to memorize the 30-60 triangle and the 45-45. Any questions about this? Does anyone want to review the 30-60 and the 45-45? Okay, so let's talk about that. So these are definitely worth memorizing. They should be memorized to help you moving forward. So we had a 30-60. The ratios would be, if we let this be 1, this would be 2, this would be root 3. The great thing about these with Pythagoras theorem, if you remember the 1 and the 2, you figure out what's this guy, you can use Pythagoras theorem to figure out this is square root of 3, which is the right triangle. And then the other guy that you need to have memorized is the 45-45. which of course is a 1-to-1 ratio because it's an isosceles triangle, and then this would be the square root of 2a squared plus b squared equals to c squared. So if you memorize these, you can pretty much do all the common ones that they expect you to know.
Wait,
So-
no matter what number it is, is that how it's gonna be, what's the
The ratio. So this is these are the ratios of a 30-60 and a ratio of a 45-45. I could write an x here, x if you want.
But then we'll put the root in terms of that.
Well, let's say, for example, so in our problem, we had to deal with the cosine of, we had the sine of pi over 3 and the cosine of pi over 3. So the sine of pi over 3, which is equal to the sine of, I think most students are more comfortable with degrees, I think. It's okay, whatever you're comfortable with. The sine of 60. So this is where you figure this out, okay. SOHCAHTOA, you have to know that. Right. So the sine is opposite of hypotenuse. So the sine of 60, opposite of hypotenuse, would be square root of 3 over 2. Yeah, so and then of course the cosine of pi over 3 would be equal to the adjacent over the hypotenuse, so 1/2. To go along with this, yeah, we definitely need to know this. To go along with this, you guys should be familiar with the 4 quadrants to know like when the different trig ratios are positive or negative.
All
So
students take calculus. All right. All students take calculus. I know something.
so
It makes a C, right? All students take.
Yeah, it's hard to do.
All students take.
Starting
All
from
here, and then
all
like
students
it
take
makes a C.
calculus. Yeah, it's like, and it looks like that. No.
so the 4 quadrants.
Oh, no. All students take calculus. She said this.
It's not a U, it's a C.
I know.
There's the
They're fine.
first quadrant, second, third, fourth.
Is that positive trig values?
So in the first quadrant, the any trig function of any value is going to be positive, right? Except where, nope, I take that back. All of them are positive. We have some funky stuff. We have some funky stuff happen like on the axes. For some of them, where they're like some of them that contain vertical asymptotes, like tan, cotan, secant, cosecant, but not an issue with sine and cosine because they're just the waves. But all are positive in the first quadrant. Okay. The only ones that are positive in the second quadrant are sine and of course its reciprocal, which is cosecant. And the ones that are positive in the third quadrant are tangent and its reciprocal cotangent.
That's my favorite.
And then the last one, cosine and its reciprocal secant. They're positive. They're the only ones that are positive in the fourth quadrant. So when I teach trig, I like to focus on this in conjunction with this. And if you know these, you don't have to memorize tables. You don't have to memorize random, what is the cosine of 60?
We learned a
Okay.
lot.
You can intuitively know what the cosine of 60 is if you know your 30-60 triangle, 45-45, and you have this down too. And it does help to have a general idea of what the graphs would look like of these trig functions. Yes, Emily? Sure. Yeah. Yep, it's available.
You guys are mnemonic for it, all students take calculus, which is fun. Make sure you get a calculus. You might be able to.
It's not working.
Yeah.
Whatever helps, guys. Whatever helps. So let's go ahead and answer. Now this was part A. Let's go ahead and answer part B. So let's go ahead and insert a page after. And let's figure this out. So part B says, show that the slope of every line tangent to the curve, this is positive. Another way to write this so that it makes more sense, I think it was easier to see the between the derivative is this. -3.
What does that have to do with the problem above?
This is why. This is why.
Wait, so it's just,
I just rewrote it.
no, I see what you
There's
did
no-
there, but what does that
Oh,
have to do with it?
with A.
Yeah, okay.
Yeah, this is a separate question. This is part B. It says show the slope of every line tangent to the curve is positive. So this, yeah, this really has nothing to do with part A.
Awesome. I thought things that don't make sense, that's my favorite.
Okay, so we continue here. So y prime would be equal to, all right, so here's chain rule. So -3 to the front. Leave the inside alone for now. Drop this down to -4 times the derivative of the inside, which is just -2. So if we write it back in the proper form, this would be equal to 6 over 1 minus 2x to the positive 4. Right. -3 times -2 is positive 6. And then when you add something to a negative exponent, you can stick it underneath and raise it to the positive exponent. Okay, so you think intuitively here that show that the slope of every line tangent to the curve, this is positive. Okay, so y prime of x is equal to this. So notice no matter what x is, no matter what real value x is, whether it's positive or negative, if this is going to be a negative value, this will be positive. You have positive divided by positive. If it's going to be a positive value, you still have a positive quotient. Positive over positive.
So, would they just want like?
Yeah, and except for x cannot be 1/2. Yeah.
If we came across something like this on the easy exam where they just want like a quick sentence about why.
Yeah, so if it asks you to describe, show that the slope of every line tangent to the curve is this, you probably would not get full credit stopping here. You would need to describe as they do similar to here and say that,
Because it's
the quotient of two positive numbers at any point x1 on the curve.
You have
X
to write
cannot
that it would
equal.
be able to be 1/2.
What's
You
that?
have to write x cannot equal 1/2. Without problem.
It doesn't hurt. It's probably not as worth as much as stating that it's a quotient of two positive numbers.
Oh, yeah.
So let's look at a few more. Let's look at a few more problems. So the reason here is because
What does that say at the end?
quotient of two positive numbers. And x cannot equal 1/2.
What is that?
Does that make sense?
Say?
Does that make sense that there's no way I can get a negative value for y prime?
Yeah.
Okay.
Wait.
Okay.
Mr. Cruz, are you bringing the class to the college and career expo? Any of your classes? You should.
Yeah, I will bring in 6th period. I plan on bringing 6th period. Yeah.
Yeah, we've got a scavenger hunt, and whoever fills it up the best of your cups, we're gonna choose, and we're doing them 2 weekly pieces. We're trying to get homecoming tickets and free basketball passes.
Okay, so let's look at some more. Let's look at some more problems.
Food, wonderful food.
Number 35 on page 153.
And we need people to help out with it, so we can go to
Number 35 says that f of u
We've got 10 minutes. You're required to help. I've done a lot of work for that.
No, let's not even do that. I don't want to do that. Not yet. Forget that. I'm just going to come out an example.
Oh, what?
So if I have f of x is equal to sine squared of cosine
I don't have any time.
3x squared plus 4. Right. So here's a good example of chain rule.
Is it like double chain rule?
And if you want, you can probably a good idea to do this.
Alright, so walk me through this.
This whole thing. So it might be easier to look at that one on the right. So a chain rule, here we go. So we're going to bring the 2 to the front, and we're going to leave all this alone.
The first. Explain to me why the 2 went over there.
Because chain rule tells us to do so.
Wait
So
a second. Do you
chain rule
do
just
this
says,
right?
bring it to the front, leave the guts lump right now, drop it down one.
I'm talking about the original, like why you took the side squared and then that. Why you moved the 2 way over?
I think it's easier to see, because it's the same thing. It's a notation thing. We discussed that earlier with, we discussed that earlier. Here, like secant squared x, the same thing as secant x, that whole thing squared. This is a notation thing. Oh, I'll do that. Okay, this drops down one. Times the derivative of the inside, which chain rule again. So derivative of sine is cosine. Leave the guts alone.
Wait.
Okay.
Times the derivative of its guts, which is negative
You
sine.
gotta keep it on.
Yep, that's what I'm demonstrating.
This is very complicated.
Not really, you just keep working it.
Oh, and then you do this on
Then times the derivative of its guts, which is 6x.
Wait,
What's cosine?
times.
This is times, this is all one line.
That was fun.
Maybe cosine
Wait, I'm confused. Why do you?
I'll go over it again. I'll go over it again. If I have time. Alright. So the 2 comes to the front. We leave this alone, drop it down one. Times the derivative of this. Right? The derivative of this is, okay, well, cosine of this, leave it alone for now, times the derivative of its inside, which is negative sine of this, times 6. You just keep working in for chain rule.
We talked, you have the cosine times and then you leave the other part the same, and then you do that, the derivative of that inside part separately?
So hold on, so times the cosine of this.
Yeah, that part.
Yeah, I think that should be inside of it.
Final set of parentheses.
Oh, and then you times again by the derivative of the cosine.
No, this is right.
Oh,
I think it's right.
got it.